All right, great. Okay, so our goal is to basically just for today understand how the web works, understand the relevant attacker models, and then understand the same origin policy, which is kind of the thing that governs how we think of web security, at least like what's going on in your browser and what you should be aware of when you're building web apps. So to get started, we're going to look at HTTP. HTTP is the protocol that sits on top of um, mostly TCP that allows us to essentially just fetch resources across the internet, right? So one of those resources, the ones that your browser fetches the most, are HTML documents, right? So each resource on the web has a URL. So if we go to, say, the old version of this class, we'd have a URL that is the thing that your browser, you type into the address bar. What is this thing actually composed of? Well, let's break it down, right? So if we look at this whole thing that when I click on a link would contain a bunch of things, including, say, the scheme, which in this case is HTTPS. Then it would contain the domain of the server that's serving this resource, the port, in this case 443. The other popular port is port 80, which would be the kind of default port for HTTP. Most of the time, you won't actually see this. This is not explicit. Most of the time, it's implicit that it's 443. In fact, if you type in most URLs, it will be hidden. So 443 is the one we assume for HTTPS. Then we have the path, in this case, /classes, so this was fall 19, CSE 127AB /lectures. Then we'd have the things that follow the question mark. This is called the query string, which is essentially a set of key value pairs. And finally, we have the fragment ID, which is the thing following the hash or pound sign. Right, so these are things that actually go to the server when we type it in. This thing is a locally meaningful thing, so it's only meaningful in the browser. Like if you type that into your URL bar, your address bar, that won't actually be sent to the server. Okay, so how does the HTTP protocol work? Well, the basic idea is clients and servers. Our client is typically the browser. Our server is just some web server sitting somewhere on the internet. They communicate by exchanging individual messages. And this is actually messages. It's not really a stream of data. So really, we send one request and we get back a response from the server. This might be, say, on a first load, an HTML page. The HTML page itself may contain kind of the structure that tells the browser to fetch more resources from the web. So it might send another request. That request might return, say, a JavaScript piece of code. That JavaScript code now starts executing in the browser. That thing might perform a request. For example, it might send a request to fetch an image. The server responds back with an image. That thing is rendered on the page, and kind of so on and so forth. Now, if you were to actually break down what the request actually looks like, so whenever your browser makes a request, it would say something like get/index and then the HTTP version, and then it has a bunch of headers in the body. So what the first thing that we send over is the method. So there are a bunch of different methods, but typically they're kind of intuitive. So basically, we'd ask the server like, "Hey, please give me like a particular thing." The way you do that is by essentially saying "get," and you can also post data, so you can send the server data. So most of the time on the web, we send GET requests, and then we tell the server, "Hey, I want the thing that lives at this particular path /index HTML, and what I'm speaking is HTTP version 1.1." So there are different versions of HTTP. This is the one that used to be the most popular. It's still, I think, like roughly 51% of the web, but we now have also HTTP2. Okay, so this is basically just plain text that we're sending over from the client to the server. Then we send a bunch of headers, which are basically key value pairs. So we have the accept header. So anything following kind of a colon is the right-hand side, which is the value. They have special meaning, but you could actually send anything. Nobody's going to stop you from sending a server whatever bad data you want. You just hope that they respond in a meaningful way. So what this request is basically saying, like, hey, I accept these kinds of content. So like image/GIF, image/bitmap, image/JPEG, and honestly, like anything else, or */*, right? The language I speak is English. I'd like for you to keep the connection alive because I'm going to send more requests, and I'm sending this from Firefox browser, so it's Mozilla /1.22. Really, this might also be the user agent that we're going to use for other browsers, like the old IE and we're trying to talk to server to host www.example.com. And the reason we specified this in the request is because that particular server may actually host multiple websites, right? So if you've use, say, github.io to host your web page, right? That thing can actually serve content for multiple users. And they do it exactly because in the request, we specify who we're trying to actually talk to, which host. And then finally, we have, a referrer header, which basically says like, hey, where did I get, where am I actually coming from? So like your browser actually sends this referrer header most of the time. There are policies around the referrer header, which we'll talk about at some other point, but basically this tells the server like, hey, I'm coming from google.com. So basically in this case, what this request is telling me is that it might be a request from clicking on a link from a Google search. And the last bit, which you can't actually see here because it's empty, is the body of a request. So the kind of the whole, this is all there is in an HTTP request. So there's the method, the path, version, bunch of headers, and the body. All right, so what does the server do? Well, it takes this data, parses it, and then responds with a reasonable response. A response might look something like this. So we're going to say, again, like what the HTTP version that our server speaks, what the protocol that we're trying to talk. Then we're going to return a status code. So in this case, we're going to say 200 OK. So anything to 200 series means this was a successful response. So I knew how to handle it. Then there's 300 series, 400 series, 500 series that all have different meaning. We're not really going to go into them, but the kind of the short bit is 300 tells the browser or the user agent or the client to redirect to a different thing. 400 usually means like I can't get this data for one reason or another. 500 usually means there is some kind of server error. Please help. Okay, so we send the status code, and then we also, like with the request, have a bunch of headers. So we have a bunch of response headers. In this case, the server might tell you what their date is, what server it's actually responding to you, what the content type of the response is. In this case, it might be text HTML, the time that this thing was last modified, the resource that's at this particular URI. And then it might tell you to set cookies, which we'll hear about in a little bit, and then what the length of this response actually is so that the browser knows how to handle it. And finally, we have the body. In this case, it'll contain some HTML of whatever sorts. So let's actually look at some real requests, because why not? Like we might as well actually get a little bit of experience pulling down some websites. So the thing that I'm going to pull up is I'm going to have my own command line client. So this is, I'm just going to use curl, and I'm going to do curl -v, and let's say https, google.com, right? Okay, so a bunch of things happened here. Most of them don't really matter, at least not for right now. So this is doing the handshake TLS, which we'll understand when we get to the crypto lecture. But here is where the HTTP bits come into play. So I'm sending a request. It says get /HTTP2. And then I'm saying I want to talk to google.com. My user agent is curl. And then I accept whatever you tell me. So this is all I sent. Then Google replied back with this response. This response basically says like, hey, okay, I speak HTTP2 as well. The status code is 301, which is a redirect. And I'm telling you to go to https www.google.com. And I'm also going to include some content type. I'm going to include, text/HTML, and then a bunch of other headers that we don't care about. And then this is the actual HTML that basically tells your browser to redirect if it didn't redirect based on the status code and location to do so when it loads the HTML page, right? So like the normal thing that your browser would do is it would see a response like this, and it would just be like, okay, thank you for telling me where to go. So I'm going to go to www.google.com. Okay, what does this tell me? Well, this gives me like a bunch more stuff. So now I made this request to www.google.com. It's probably the same server that we were just talking to, but now I get like a little bit more information. So now I get an HTTP 200, right? So this is an OK. It's telling me what the date is, a bunch of other headers, and then it gives me the actual HTML page for google.com, which is surprisingly gross, right? So that's kind of cool. Okay, so this is how like you can play around with as a client. let's also do a server example. So what I'm going to do is I'm going to have my own server. So I'm going to do nc, actually, I'm just going to cheat, nc-l. Okay, I'm not going to cheat, I guess. -p 8080-c. Okay, so this is called netcat. It's basically a program that is a nice wrapper around socket. So now I have a server listening on port 8080, just waiting for anybody to connect. So what I'm going to do is I'm going to pull up my trusty browser, and then I'm going to go to HTTP localhost port 8080. Great. Now, nothing is loading, and that's because my server hasn't responded. So like, let's look at what my server is doing. Here's my server. Well, this is a request that I got. So this NC just prints things out. So it's telling me like, hey, I'd like to respond to this. So let's actually respond. So what we're going to do is we're going to respond with HTTP/1.1, and then we're going to do 200. Okay. Then we're going to say content type is text/HTML. Then we're done with header. So we're going to put another new line and caret return, and we're going to reply with some HTML. So I'm going to just do HTML script alert hi, and then script. Maybe we'll have a body that says hello world body /HTML, and then I'm done with my body. Control D. When I'm done with this, the server actually crashes because that's all it does. It just terminates. Let's actually switch to our browser to see what happened. Well, this is what's going on in my browser. I got that alert, so it's rendering. It's rendering that page that we sent, which contains the script, and then it's done running the script, and it prints the body. And if we decide to look at the source, well, we can't because there's no actual source. But I can pull up the inspector here and look at what the server sent us, which is exactly what we just typed in. Right. So you can imagine, like, with a few clever scripts, you can write your own like little server with just a wrapper around this netcat thing that I was toying around with. You probably shouldn't, because it'll be super insecure, but this is like a quick way to figure out what HTTP looks like at the wire. Great question. So how come we didn't have to specify the content length? So in general, the content length is an interesting thing, because the content length would normally tell you like, hey, what's the length of the body, right? It turns out browsers are really permissive. So what I actually sent was a totally like ugly and gross response, but browsers are very permitting. In fact, if I had all kinds of weird, bad HTML, the browser would still do its best to render the thing. So browsers are happy to basically take all kinds of garbage from servers. And unsurprisingly, this is largely because historically servers have been terrible at responding with well-formed both HTTP responses and HTML. And previous user agents and browsers have sent all kinds of like crappy requests too. The other thing is we really don't want to necessarily trust the content length, because that right, like, we're getting something over the network. This could be a potential actual vulnerable server that we're talking to. So we'll probably want to figure out what our content length is anyway. But yeah, the real reason is they're very permissive. Okay, so we only looked at one kind of request, namely GET requests. And kind of the semantic meaning of GET is that we're going to get the resource at that specific URL. It's supposed to not have any side effects server side. If you want to perform side effects, you will use one of the other HTTP verbs. So for example, if you use the post request, the idea with post is like you're telling the server to create a new resource at that URL. With put, what you're basically saying is like, okay, there's already an object at that URL. Replace its representation with the payload that I'm including in this HTTP request body. Patch says like actually only update a part instead of like a full thing that put would be used for, and then delete would basically say like, hey, please delete the thing that's at this URL. So these are really nice, right? Like this is essentially like a really nice database interface that a browser would normally perform. In practice, this is kind of a mess, and it's historically just kind of been not the greatest thing. Partly because browsers would only support really get and post for many years. So people ended up abusing post to do put, patch, and delete. So basically, anything side effecting would actually be done with a post request. If you want to tell the server like, "Hey, this is actually a delete" or "This is an update," you would typically include it in the actual body. So like, we kind of like don't use these verbs the way we should be, but in the end, kind of you can write your server as if you did and have essentially programs in between rewrite these requests to make it seem like you got a delete request. So these are called middleware. So browsers are kind of a little bit of a mess. Servers are also a mess. So for example, GET requests should not change server state. The idea is you should be able to send a GET request to a server, and the response you get back should basically be the same all the time. In practice, that's actually super duper not the case, right? So you all get emails from people in places you don't want, and at the end, if they're legally binding, they have a link that says unsubscribe at the bottom, right? When you click on that link, that actually sends a GET request, right? And in fact, you want that thing to have side effects, right? So we kind of abuse GET requests as well for performing server side effects. So it's kind of like a mess, but we have the web and it kind of works when it's not a total disaster. In practice, we also need state, right? So HTTP is a stateless protocol. We send requests, we get responses. We send requests, we get responses. There is no state carried anywhere. The way we add state to our web applications, for example, if we want to do session management, like logging into a website, having shopping carts, having preferences, themes, all kinds of different things. The way we typically do this is using HTTP cookies. Cookies are just tiny amount of data that the server sends to the browser, and then the browser basically just echoes this piece of data back to the server every time you make a request. So, for example, what we were seeing earlier in our response body, we have these set cookie headers. These set cookies tell the browser like, "Hey, please set a cookie." And in this case, we have two cookies. One is the tracking ID, which has this giant number, and then one is the user ID, which is this other number, right? So this is kind of like, please remember that it's this user, and this is their tracking ID. And then with every request we make to that server, we end up echoing that cookie back. So we send a cookie request header that just says, again, tracking ID is this big number, the user ID is this other big hexadecimal number, right? So it's just ping ponging back. This is how we do state. It's not the most efficient thing, but it is what it is, and that's kind of a thing that we have to be aware of when we're thinking about security, because that has a bunch of different implications. The other thing that I wanted to point out, and this is totally an aside, but we already saw it with curl, is that half of the web actually uses HTTP. HTTP2 was released in 2015. It basically doesn't require you to change your web app at all. It's only largely giving us a more performant web. So it allows us to pipeline requests for multiple objects. It lets you actually multiplex multiple requests over the same TCP connection. It lets us actually do header compression, right? Because what you were just seeing is a text protocol, right? Which is super inefficient. We can pack these things to binary and actually do real compression. We can also have the server send the client messages, as opposed to always have the client ask the server for different things. So we can have the server push data. And there's also HTTP 3, which is an internet draft as of basically this month. So yesterday. And this uses QUIC instead of TCP. So it's basically HTTP over QUIC, which is kind of this new fancy UDP protocol that addresses, again, more performance issues. And your browser actually supports all this. You can turn it on. It's just not on by default yet. Not sure if it is for Chrome, but I assume it's not even for Chrome yet. Okay, so this is mostly an aside. It's just things to be aware of, because you're going to largely look at HTTP 1 traffic, but HTTP 2 and 3 are a real thing. and will be more so going forward. Okay, so we have HTTP. We kind of have this protocol on top of which we build a bunch of web applications. So what's going on? How do we go from an HTTP response to executing code in the browser? To understand this, we're going to have to understand how the browser, or like what the browser execution model looks like. So when we look at a page, each page, right, when it loads this HTML document, will load some content. So we parse the HTML and then we run whatever JavaScript is on the page. In parsing HTML or executing JavaScript, this might result in fetching more resources. These will be called sub-resources. So for example, we may load images, we may load CSS, we may load more JavaScript. This browser or this page can respond to different kinds of events. So for example, we can interact with the browser by clicking, right? So then there's JavaScript code running when there's on-click events, on mouse over events, when the page loads, when certain resource was loaded from the network, on different timing events, so on and so forth. So it's basically a full programming environment, right? And I think most of you have seen this. If you haven't, that's totally okay. You've at least interacted with these things if you haven't programmed it. The browser is different from, I guess, the previous execution models that we've looked at, in that it has a nested execution model, right? So like each window or page can contain subpages within, right? These are called frames. These frames can be from totally different sources. So it can be from a very different server. They can be embedded rigidly, so we can actually have direct frames. Or really, what we're going to have is what are called floating inline frames or iframes. This is basically what most websites use, that they don't even look like they're loaded from a different page or a different source, because they look really pretty and can be like resized according to whatever like the outer page styling looks like. Right, so we can have, say, A.com embed pages from B.com and C.com, which themselves can further embed pages from D.com and so on and so forth, right? And these are all kind of, you can think of them as different UIDs if we want to think about this in the context of kind of the old OS model. And we're going to have to think about how does the browser actually isolate these things, right? Because they're coming from different servers, right? And you can imagine bank.com and something else. You'd want to have that actual isolation in the browser. Otherwise, kind of all bets are off, and we're like in a totally doomed world where visiting Reddit results in somebody stealing your credit card numbers. Okay, so we use these iframes for many reasons, but like the primary reason is we want to delegate screen area to content from another source. If you've used something like Yelp has Google Maps typically embedded. That's typically embedded as a frame. Sometimes it's running directly, which is a little scary. On a typical website, like a news website, we'll have iframes from Twitter and things like that. So there's all kinds of reasons for having this different content within the same the same kind of drawing area. And again, we want isolation because these things are different parties. And I guess the one last bit that I want to mention is if an iframe breaks, kind of like one of the nice bits is we do have this isolation property that like, hey, if an iframe crashes, the rest of my parent page still executes normally. This is not necessarily true for all browsers because they might actually be running within the same OS process underneath the hood. But most, at least Chrome and Firefox, have moved to a world where at least iframes of different origins, which we'll know what an origin is in a little bit, but basically different sources, are put in separate OS processes so that these things are kind of isolated crashes. But more importantly, you can't use something like Spectre to get at content from a different origin because these things are in a separate process. To a degree, we can talk about how you would steal it even then, but at least that's a good approximation. Okay, so within this process, within this browsing context, JavaScript can access and modify the page, right? Like you've all interacted with these really fancy web applications. The way they do this is, or at least the way the browser lets JavaScript do this, is by exposing an object called the DOM, so the document object model, which is basically an object-oriented interface to like modifying the different tree representations of the page, right? So this lets you actually access the window, the document, and a bunch of other things that let you basically render different content in different places and respond to different things according to either user interaction or network requests or things like that. This includes the BOM, or the browser object model, which is not like the thing that you actually see. So, for example, um, uh, the history is something that you don't have directly access to, but or full access to, or like, cookies. These things aren't directly things that we think about as part of the DOM. They're more like the browser state things, but they're pretty important because we need to navigate, we need to access cookies. Sometimes we need to even have local history information so that we know how to handle back and forward button clicks. Um, and we might also want to be able to access windows of separate tabs or pop-ups that we've created. Most of the time, all we're going to care about is this DOM model, where basically we just have a bunch of JavaScript that lets us modify the page tree, and it looks something like the representation on the left. Okay, so if you haven't played with the DOM or written much JavaScript, here is maybe one of the simplest examples where we have, say, some HTML that contains a body. This body contains an unordered list that contains one item. Well, if we had, say, a script in between this item and the rest of the body by the end of it, this script could, for example, insert another item, right? So one thing it can do is it can use the DOM to get an element. In this case, it can get element T1. What's T1? Well, if we look at the actual, HTML, it's this UL element whose ID is T1. So this is kind of like our list. Then we can create a new item. So document that create element lets us actually do that. In this case, we're specifying the kind of element we want to create is a list item or an LI. Within this list item, we're going to want to actually insert item 2. The way we have to do that is we have to create a text node. And with this text node, we'll have content item 2. And then what we're going to do is we're going to insert this new item into the list, and we're going to append to this item this actual body, which is the text. So it's a little bit gross and ugly, but at the end of the day, we get the item 2 that looks kind of, when printed out in HTML, exactly like this, but instead of 1, we have 2. So if you haven't seen this, I recommend just playing with a little bit of JavaScript. The web assignment might be enough, but it's a thing that you'll hit at some point or another in your life. So might as well get started now. Okay. So we've just looked at super simple kind of interactions. Real websites are super complicated. So here I have a screenshot from LA Times from 2019. There's all kinds of different things that are happening. It, like, at this particular point in time, it loaded 550 resources from 270 IPs from 58 networks, 8 countries, so on and so forth. Have any of you actually looked at what your typical page loads? All right, if you haven't, here's what we're going to do. Let's go to latimes.com today. So we're going to pull up this thing here. I have my browser, and then I'm going to pull up, I guess, let's see, the network. I'm going to just close this thing here. And this is with an ad blocker. If I turn off the ad blocker, it would probably load quite a few more things. But this alone is, I hope, let me hide this again, kind of a good example of this is a lot of stuff that's being loaded. It took 5 seconds, 7 megabytes were loaded. That's quite a bit. I don't have, let me see if I can, well, okay. You'll just have to trust me that if you actually turn off the ad blocker, this is way, way bigger. And it's really, really actually scary, right? Like, if we're thinking about what's going on, well, we have tons of third-party ads. We have Google Analytics, which is essentially some kind of spyware, whether you want to call it that or not. We have iframes that are like loading ads. We're going to have libraries like jQuery. We're going to have our own local scripts, right? Because we're also trying to build this web app. Then we have extensions, right? So I mentioned one of the extensions that I have is an ad blocker. I have a few other extensions. These extensions also run within these pages. So there's like so much code running in your browser. It's almost amazing that it actually like works. Okay, so I hope now you have some sense of kind of how the web works, right? So there's HTTP. On top of that, we build these really fancy web applications that talk over the network, load resources, and run a bunch of code. So what are the attacker models that we should be thinking about when we think about the web? The simplest one is the network attacker. This has been kind of slightly less relevant nowadays attacker, but you'll still have to be wary of this, especially if you're building a web app. And the reason for it is because it's kind of like almost the default. So the default, when you pull up a web server like, I don't know, Node.js, is that thing will listen on port 80 or whatever port you tell it, and it doesn't do any encryption, right? So HTTP here is kind of the insecure, and browsers are finally complaining about this. But the basic idea is if you have a network attacker, this network attacker sits on the wire, and if we're serving content over HTTP, which means this is totally unencrypted, which means the attacker can see and modify things in between, that's something to be totally worried about. Even with HTTPS, which is the encrypted and authenticated channel, and you'll understand what those mean, what those words mean in a couple of lectures. Even then, we have to be wary of a network attacker because they might still mess with this communication channel. But for most of this class, we're not going to look at the network attacker. We're just going to see at the end of if you don't actually serve your web app on top of a HTTPS, what kinds of things can really go wrong. And your IoT devices probably do it over HTTP, so it's something to be worried about. The one that we're really going to spend time on is called the web attacker. So here, the idea is the attacker is running in your browser. So you might have clicked on a link that you shouldn't have clicked on that navigated you to evil.com. You might, let me, before I show you the gadget attacker, you might load a page that's not necessarily evil. So you might load a page that's like example.com, but you might have an iframe that example.com loaded, and that thing actually contains the attacker, right? So this might be, for example, an ad. So we're worried about, like, how to defend against this case. So if we're building a web app and loading potentially untrusted ads, how do we build a secure web app like that? We're also worried about the other case where we are, trustworthy, but some evil website actually embedded us as an iframe, right? So now the attacker is the outer frame, the victim is within. Or, we may have cases where, you visit a shady website, it's in a separate tab or separate window from your example.com, right? So this is kind of the web attacker model. We're going to see different versions of this and how things can go wrong and how we defend against these models. The last one that I had a little bit earlier here is the gadget attacker. So here, the idea here is we have a web attacker, so kind of the same things that we just saw, but their capabilities are slightly more limited to just injecting some limited kind of content into the page. So the iframe case is a special case of this, but you can imagine loading untrusted images, loading HTML that you then want to parse, or even JavaScript from the attacker. We're not going to really talk about the gadget attacker. This is something that you may be concerned about if you're trying to build web apps where you're trying to run code supplied by other people client side. So if you're into this, I'm happy to talk offline, but for the rest of this class, we're going to focus on this model where we're either visiting a page that the attacker convinced us to visit, or we visit a victim page where they might be embedded within. Okay, any questions on this before we move on from the attacker model? All right, so these are the attacker models that we really care about. And the web one is the most prominent one. What questions do you have? Why don't I take a little bit of water while you think of questions? Okay. Well, if there are no questions, that's okay. But if something does come up, please just feel free to shout out. Okay. Okay, great. So is loading PHP either locally or remotely a valid attacker model? So here we're talking largely about attacker models within the browser. PHP is a server-side um, scripting language. So we'll see more about how to deal with PHP, and if not the next lecture, the one after, where we deal with with attacks on servers. We're largely looking at attacks client side for now. Um, but in general, you don't want to load PHP remotely. So I would avoid that at all possible. Using PHP alone is already kind of scary. Um, okay, other questions? All right, so now you have some sense of how the web works. We know like a little bit of where the attacker is. We're going to look at it in more detail as we go through understanding the same origin policy. Okay, so the easiest way to talk about the same origin policy is to think about our previous lectures, which were on, or at least the one on isolation and OS security, right? So kind of like one of the things that the browser lets us do is it lets us, or intends to do, is it wants to let us safely browse the web in the presence of attackers, right? So that the attacker model that browsers assume is that like, look, like you are visiting 4chan and you're visiting bank.ch at the same time. Either one of these can be actually malicious. So the browser assumes that it's dealing with untrusted content, right? So like one of the things that we'd like to do is much like in the OS world, we want to separate two processes like Zoom from KeePass. We want to isolate 4chan from bank.ch, right? And part of the reason we want to do this is because right, Zoom might be malicious. I might care about Zoom accessing KeePass, which is say a password manager. Similarly, I'm worried about 4chan potentially, or people's rendered HTML and JavaScript on 4chan from getting at my bank stuff. Now, in the OS world, we have UIDs, SecOnBPF, then virtual machines, a virtual memory, and we have file ACLs, and we have kind of, again, UIDs that come into play when we're trying to access different resources, right? So between these two, we have virtual memory plus UIDs. Between this and this, we have UIDs and ACLs, right? So this is kind of like this is how we do isolation at the OS level. In the browser, what we have is the same origin policy that prevents 4chan from accessing your bank.ch tab, and we have the same origin policy that ensures that when you write to files which aren't really files, they're really cookies, or when you talk to the network, 4chan and bank.ch are isolated from each other. So, okay, this is at a high level what we have. So the same origin policy is kind of like this really vague idea, but it's a pretty good one, right? So kind of like the idea is that we're going to define security principles as origins, and an origin is basically our way of drawing a trust boundary, right? So like we saw different ways of drawing trust boundaries in the OS model. One is the process, another one is the library. In the browser, it's the origin. So the origin is how you draw the trust boundary. And this basically comes down to three things. So we define an origin as a triplet. It's the scheme, the domain, and the port, right? So we have, say, HTTPS, ucsd.edu, and port 443, right? So basically what this basically is saying that HTTPS, ucsd.edu, 443, that anything that has that origin should be isolated from anything else that has a different scheme, a different domain, or a different port, right? So this should be different from HTTPS, mit.edu 443. And kind of the high level goal is to isolate content of different origins. So what we really want is two things from the same origin policy. So what we want is confidentiality, which basically means that a script, when you go to evil.com, should not be able to read data that belongs to bank.ch or that lives in a bank.ch page, right? So we want to make sure that evil.com is totally isolated from bank.ch. I can't get at your account information. The other one that we want is integrity, right? So again, script from evil.com should not be able to modify, the page of bank.ch or modify your cookies for your bank. Make sense? So this is at a very, very high level. And in practice, it's quite a bit uglier, but at least at a high level, what we want is, evil.com isolated from bank.ch, isolated from Spotify, isolated from Zoom, and everything else, right? So you kind of have like this model where we have different turfs belonging to different origins. Okay, now the reality is there is not one same origin policy. There are many same origin policies, but together we call them the same origin policy. So there's a same origin policy for the DOM, so how you access the DOM of different pages. There's the same origin policies for talking between two iframes, for example, between message passing. So this is done using the message pass, the post message API. So there are, restrictions on who's allowed to see messages when you send them over, depending on how you use this particular API. There's the same origin policy for network access. So when your page makes a network request, whether it's through JavaScript or whether it's by embedding elements into the page, like, image source, whatever, to fetch an image, there's a same origin policy that says like whether or not you're allowed to look at that particular response. And there's also a same origin policy that says like what you send when you send that particular request. In particular, that comes into the cookie world. So when we send a request, we may send cookies. We want to actually look at what cookies do we send when we make a particular request. And then there's like the same origin policy even for style sheets and fonts. So for example, when you load a style sheets, are you allowed to look at the source of that style sheet or not? Right. So those are kind of things that we care about, because if you load a style sheet from a different origin, right, you might imagine that origin saying like, no, you're not actually allowed to look at this thing. You're only allowed to use it. Okay, so let's look at some of these examples. We're going to start with maybe one of the most important, which is the DOM, right? So each frame in a window has its own origin, and frames can only access data within the same origin. So this includes the whole DOM tree, local storage, cookies, so on and so forth. So for example, here I have, three different frames. I have the top level frame, which is a.com and 443. And then I have there two iframes. One is evil.ch. The other one is another a.com. So because these two are of the same origin, this outer page can modify this iframe here. And conversely, this iframe can modify the outer page here. Okay, so these two are essentially of they're of the same origin, so that you can get the DOM of the iframe. So whatever the tree may be here that represents the page, you can modify it. You can inject scripts. You can add event listeners, so on and so forth, and that iframe can modify the outer page. Right? Just because one is embedded in the other doesn't make it any more privileged or less privileged. But the thing that we can't do is do this cross origin, right? So for example, the outer page can't muck or even look at the DOM of that evil.ch iframe, and that evil.ch iframe can't look at the parent a.com page that includes the DOM and everything else. So it can't muck with it or read what's in it. And same goes for sibling iframes, right? So evil.ch iframe can't mess with the a.com iframe. And again, they're just cross origin, so these kinds of things should not be allowed. Okay, but sometimes we actually want to communicate and across these iframes, right? Like this is like why we have iframes. We actually want to like build web apps that are kind of content rich. So the way we do that is we use message passing. So I mentioned this a little bit earlier. So if you want to send a message to another frame or parent window, the way you do it is you get a reference to it, which in this case would be, say, target window, and then you use the post message API to send whatever message that is. So that message can be anything that can essentially be serialized across these context boundaries. And then you also specify here the target origin of the window that you're intending to send this to. We're going to get into why you need to specify this thing, but this basically says like only deliver this message if the origin of the window is this origin that I'm giving here, right? So I might specify, http://evil.com. Make sense? So this is for sending messages. To receive messages, what you need to do is you need to first define a function, in this case, receive message, and essentially register this function with the global event listener, which basically says like, hey, whenever I get a message, please call receive message. Internally within receive message, the first thing that you want to do is check to see like, hey, who sent me this message? What's the origin of the context that sent me this message? The way you do that is by looking at event.origin, and you want to make sure that you're only getting messages from iframes or outer pages that you trust. So you kind of should include something like the explicit origin, like http example.com, and then do your actual business in the function. So this is kind of a little bit gross, but basically, because the browser is essentially forcing you to do a little bit of the validation yourself. If you don't, you get into all kinds of weird attacks, which we'll talk about in the next class. But essentially, the things that you need to check are origins, and specify origins when you send messages. Okay, so that's the same origin policy for message passing in the DOM. What about networking? Well, let's look at HTTP responses, right? So again, pages can perform network requests across origins. They typically do this. This is pretty common. And in fact, the same origin policy doesn't prevent you from sending a request to an arbitrary server on the internet, right? So like the same origin policy says nothing about leaking information from your own context. So you're totally allowed to leak whatever you want from your own context by just encoding it in the URL or in the request body or whatever else you want. What the same origin policy does say is when you get a response from a server, whether or not you're allowed to look at that response. And this depends on the actual response type. So the short of it is that except for documents, when you get as responses, you can learn some information about the response. If you perform an HTTP request in JavaScript with the XML HTTP request API or with the fetch API, and you get back a document, an HTML document, you can't inspect that thing at all, right? And but for other things, you might be able to inspect once you start rendering them. So let's take a look at different kinds of content types that you may get from a remote server. Okay, so the simplest one or the most common one is HTML. So if we load HTML in the form of an iframe, right, like we're not actually allowed to inspect or modify the content of that thing if it's cross-origin. So when A.com performs a request to B.com, there's an HTTP request being sent. B replies back with a HTTP response. This response, if the way we perform this request is by creating an iframe source equals blah, 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 then the browser will create a box and render that HTML page in that box, right? But importantly, we can't look at that thing. So we can't inspect that at all, right? This is a cross-origin HTML document. So A.com can't look to see what B.com replied back with. Scripts are a little bit different, right? So when we load scripts using the script tag, that script, say if we're in A.com and loading it from A.com, it has those privileges. We can always print that script with a toString. We can do this for cross-origin scripts. So for example, when we load a script from fastly.com, so Fastly is a CDN, this is a reasonable place to load scripts from. We can kind of like learn some information about that thing because it's going to execute, right? So whatever that JavaScript code is doing might leak some information by modifying objects. But the other thing to be worried about is if we load scripts from evil.com, that thing runs with the privilege of the page, right? So a.com loading a script from any of these three different origins will have the same privilege, right? So the way to think of this, if you want to map it back to our previous lecture, it's essentially taking a binary blob and calling dlopen and executing it, right? So this is what we're doing. So like in the JavaScript, in the web world, it's like really fast and loose, right? So any script loaded from any origins runs with the same privilege of that page. There's no way to distinguish, a.com from evil.com scripts if I've included them with a script element. Okay, but if we're worried about when we say send when we send some code to some server we don't some browser we don't trust, right? So if say if evil.ch didn't want you to be able to inspect their script, right? It gets pretty tricky because of things like this that are available to like the a.com. So a.com can take functions that are defined in this particular JavaScript file and just print their source to try to figure out what the source of that evil script is, right? So you probably, as evil.ch, if you're trying to hide a script that you're running, do all kinds of mangling to prevent these kinds of inspections. So this is an example of kind of the same origin policy being a little bit too loose to some degree, right? Because we have no separation of these different scripts from different origins, but also kind of a little bit clunky because if we want to look at the source, we have to do these things like toString. So it's a little bit leaky. We can't completely like disallow you from inspecting cross-origin content if it's loaded as a script, right? And the thing to be kind of aware of is sometimes an attacker might try to load not JavaScript but something else as JavaScript, and and how that thing executes, they might be able to infer like what the content of that thing is. Okay, so enough about JavaScript. What about images? Well, when we load images, so if we're say a.com loading an image from a.com, this is an image that we can actually inspect the pixels of because it's the same origin. But if we say load an image from fb.com, this is a different origin. We can't actually inspect the pixels, or at least not in a way that lets us do anything meaningful with it. What we can inspect, though, is say the image width and height when that thing is rendered, right? So for example, suppose fb.com replied with one image or the other, depending on whether or not the user is logged in. Well, then when we get an image into our page, that image may be of 80 pixels or 40 pixels in width. And if we have JavaScript code that is trying to figure out what this image looks like, it might do, hey, is the image width greater than 40? If it is, then I know that the user actually is logged in. Otherwise, they're not, right? So this is like one way evil kind of web attackers that are running in your browser as ads or something else can potentially try to figure out whether or not you're logged into a particular website, right? Because that website may reply back with different content, depending on whether or not you're actually logged in, right? So like just visiting a.com might reveal to a.com if you have a particular account on Facebook and whether or not you're logged in. Okay, so that's all the same origin policy I want to talk about, except for cookies. Fonts and CSS are similar. So in the rest of this lecture, if you're not heading out to watch the Angela Davis discussion, is going to be on cookies. So cookies, again, lets a server store small pieces of data on the client. And the client just echoes this piece of data back anytime the client loads a page, right? So it's super duper important if we're, say, browser implementers to only send cookies to the right server, right? And this is super important because we use cookies for all storage. It's a little bit of a lie, but for like all important storage. So if I send, you know, your bank.com cookies to attacker.com, suddenly the attacker can log in as you and steal a bunch of your really sensitive information. Okay. Now, the thing that's a little bit awkward, so we already kind of saw a pretty complicated same origin policy for different parts of the browser, right? Like between the DOM, HTTP response, and even JavaScript. The same origin policy for cookies actually uses a separate notion of origins. So our origin so far has just been this triple, the scheme, domain, and port. The cookie same origin policy doesn't include the port. Instead, it contains the scheme, which is an optional thing, then the domain and the path. Right. So, for example, this is a valid cookie valid cookie origin. So it would be HTTPS. It would contain the domain, and then it would say have the path for previous run of this class, and this path would be different from the current run of this class, right? So instead, this year would be /classes fa20 /CSE 127. Okay, now how do we use these origins? Sorry about that. Well, it comes down to basically just how do we set and get cookies, right? So page can set a cookie for its own domain, and any parent domain, as long as the domain is not a public suffix. So we'll find out what this second part means, but at least the first part is already kind of creepy because it means, Dayon.ucsd.edu can set cookies for, ucsd.edu. And sorry about the writing. It's atrocious, but I hope the audio track makes up for it. Okay, so how do we read cookies? Well, a page can read the cookies, again, for its own domain. So dayon.ucsd.edu can read dayon.ucsd.edu cookies. And ucsd.edu can read its own cookies, right, for ucsd.edu. But a page can also read cookies for any subdomain. So, for example, ucsd.edu can read dayon.ucsd.edu cookies. The thing that should frighten you a little bit is, something like csc.ucsd.edu, like our CSE website, can set cookies for all of UCSD, unless ucsd.edu is on a public suffix list, which it's not, right? So somebody can visit your page or like my page, and I can change your cookies for all of UCSD, right? So that's a little scary, unless UCSD is on the public suffix list. So what is this public suffix list? Well, this list is maintained by, I think, Mozilla. I think it's still Mozilla, but it was, at least for a while, Mozilla. It should probably still be Mozilla for a little bit. And you can go find this out. So if you just search or go to publicsuffix.org, you'll be able to get the list. The list is basically a list of domains which are called a public suffix. So the idea is, hey, if that domain is on the public suffix, then you shouldn't be allowed to set a cookie for it, right? So if ucsd.edu was on this list, then csc.ucsd.edu shouldn't be able to actually set cookies for this. So let me actually just pull it up. Might as well look at this. So public suffix list. Let's go to that. Let's Google this. Great. Okay. So I'm going to look at the actual list, see the list. So GitHub.io is one that I wanted to basically point out, right? So great. So this is basically saying that, hey, if you go to my project.github.io, you shouldn't be able to set cookies for your project.github.io, right? We should treat those things as totally separate entities because they actually are, right? So this is kind of an important thing to have on the list, because if we didn't, then the browser would happily let dayon.github.io set cookies for github.io, which means you're logged in, so I can mess with your cookies or read your cookies. I can also mess with somebody else's website if they're hosted on github.io. All right. Do we have any questions on this? Have y'all seen github.io or played with github.io? If you haven't, it's just a way of hosting pages, your own sites on GitHub. All right, excellent. Okay, okay, now we know when we can set cookies and what domains of those things are, and when we can read them. When does your browser actually send cookies? And when it does send cookies, which cookies does it send? Now, up until this year, the answer is, or would have been, that browsers send all cookies that are in the URL scope. And what this basically means is if the cookie domain is in the domain suffix of the URL, that is the URL of the thing that you're sending the request to, then we're going to send a cookie. And if the path is a prefix of the URL path, so if the path of the cookie is in the URL path, then we're going to send it. So if those two conditions meet, send cookie. Modern browsers, so the latest Chrome and Firefox, and I think Safari, they only do this when the same site attribute of cookies is set to none. We'll understand what same site cookie means by the end of this lecture, but I wanted to point out that this is how browser used to work. They're slightly more secure now because by default, they don't send cookies as widely as they used to. Okay, so let's actually go through the exercise of figuring out when do we send what cookie depending on this domain and path prefix. So to do that, what I'd like to do is get iPad and chat, and let's go through this exercise. Okay, so here I have 3 cookies, which, and I'm showing you here the HTTP responses that were used to set these 3 cookies. So the first one is for domain login.site.com. It has path /. The second one is for domain site.com. Again, path is /. And then the third one is for domain site.com, and the path is my home /my/home. Right. So, okay. So if we make a request to check out that site.com, which of these cookies do we end up actually sending? Do we send the first cookie? So we're making a request to check out that site.com. Do we send the login.site.com this first cookie or not? Yeah, so the answer is actually no, we don't. Why not? So we also don't send this one, but we do send this one, right? So if we look back to our rules, so we send a cookie if it's in the URL scope. So that means that the cookie domain is in, so the cookie domain is the domain suffix of the URL domain, right? So is the cookie domain here, login.site.com, a suffix of checkout.site.com? The answer is no, right? What is it a suffix? Is site.com a suffix of checkout.site.com? The answer is yeah, right? So this is why we send this one, but the reason we don't send this one. The reason we don't send this one, even though the domain is actually a suffix, is because the path is actually not a prefix of the URL path, right? So if this was /my/home, then we would have sent it, but otherwise we don't. Okay, so let's now look at the second one. Let me erase these things here. So we're sending a request to login.site.com. Do we send the login.site.com cookie? Yeah, right. So we send this one. Do we send the site.com cookie? Yeah. Okay. What about the last one? Do we send the last cookie? No, right? And we don't. And again, the reason we don't is because of the path, right? The actual domain is a suffix. Okay. Now we have login.site.com/myhome. We're making a request there. We again send the first because the domain is a suffix and the path is a prefix. The second one we also send because again it's the domain is a suffix and the path is a prefix. And now we also actually send the site.com cookie because the domain is a suffix and the path is a prefix. Okay, and lastly for this one, we don't send the first cookie, and we don't do that. Why? The path, right? So the path is not a prefix. What about the domain? Oh, sorry, the other way around. The domain is not a suffix. We do send this one. The domains are the same, and the path is a prefix. And again, we don't send this one because the path is not a prefix. Okay. If these didn't completely match up to your intuition, what I would suggest doing is just looking back at this particular slide and basically going through these two rules and seeing like, does it match or not? And going through the exercise of filling in that chart. I think it's a worthwhile exercise, kind of thinking through the quirkiness of cookies. Okay, so we have this nice path that seems to give us some finer kind of notion of isolation, right? So if I go to ucsd.edu/a, that seems to maybe be isolated from /b, right? Because we're not going to send cookies unless one path is a prefix of the other. So up until now, we've been just talking about the same origin, or the notion of origin being kind of where we delineate the trust boundary. Is it actually the case that this path gives us a slightly finer grain than the same origin that we have from, say, the DOM? What do you think? Like, are we tied to the triplet, or can we use this path as a finer grain thing? Like, if you were a web, developer, would you suddenly trust this path as an additional trust boundary? Right. So, would you trust, or treat pages that live on ucsd.edu/a and /b as totally isolated from each other? Yeah. So, like, I think the answer is no, and I want to just give you basically like one concrete example of why not. Right. So the cookie same origin policy. So if I have, say, ucsd.edu/dstefan, this is isolated from somebody else's, in this other case, the other one of the other security faculty, Nadia, right? So I don't see I don't see cookies for Nadia, right? If you go to dstefan/dstefan, right? But we can actually get at those cookies, right? Even though, like, when you visit this page, you're not going to see cookies that have this path. The way you can get at those cookies is, well, we're going to create an iframe, right? So if you go to my site, my site can create an iframe to https CSE web ucsd.edu/tilde-nadia-h. This is going to be an iframe that, when inserted into the body, will be of the same origin, right? According to the DOM same origin policy, right? So what does that mean? Well, it means that this iframe I can completely inspect, right? It's treated as the same origin, so I can look at this DOM object. I can, modify it. I can also just inspect things. And one thing I can inspect is I can look at the iframe, content window document dot cookie. So I can just get at that cookie. So that particular iframe will load the cookies for Nadia H. And by embedding it in an iframe, I, as Dan, can get at those cookies too. So this is like a thing to, in general, be wary about. If you kind of take much away from this lecture, is the same origin policy is pretty reasonable. Anybody trying to do something finer grained should be looked at with a little bit of a squint. Okay. The other thing that I want to highlight is, again, the same origin policy for scripts is very loose. So when you load a script on your page from, say, Google Analytics or whatever third party, doesn't really matter. That thing has the same privileges as your own scripts running on that page. So it can actually just look at document.cookie. And because the same origin policy doesn't prevent us from leaking data, if you accidentally loaded a malicious script, that script can totally leak your cookies, right? So it can either send it directly with JavaScript APIs, or it can say create an invisible image whose URL points to evil.com/cookies with your cookies embedded as part of the URL, right? So JavaScript runs with the same privileges. There's no separation. So you should be wary of the JavaScript code that you load because it'll have access to these cookies. Unless, of course, you have cookies that when you send them over to the browser, you've specified to be only visible to HTTP. So if you specify the HTTP only attribute, this basically means that anytime the browser makes a request on behalf of the page, because it's, say, loading images or whatever, it will send cookies, but it won't expose these cookies to JavaScript. So basically the page will keep sending cookies when you make normal requests, but JavaScript code running in the page can't actually look at what those cookies are, right? So this is basically making cookies opaque or transparent. So HTTP only is a bad name because now we typically have HTTPS, but the idea is that they're not visible at the application layer through JavaScript. Now, the last kind of bit that I want to get into is the same site. So I mentioned that new browsers don't send cookies the way we just talked about. And the reason they don't do it is because they're trying to have some sensible protection against a class of attacks called cross-site request forgery attacks, which we'll get into in 2 seconds. So to motivate why we care about same-site cookies, let's suppose we visit evil.com. And at some point, we also visited, bank.ch and 4chan.org, and our browser has 3 cookies stored that it's stored on our behalf. In particular, it has the evil.com, the bank.ch, and 4chan.org cookies, right? So we have those three cookies. We visited this page. Now, the browser is going to make a request to bank.ch. And here, what we're going to do is first talk about the classical case, which is the one that we just saw when same site is basically set to none. So let's make a request. The way we're going to make a request is by having an image source and then set it to bank.ch. So my question to you is, which cookie is actually being sent to bank.ch when we make this request from the evil.com page? There's 3 traces. Keep going. Keep typing. If anybody agrees or disagrees. All right, fine. Yeah. Okay. So yeah, that's right. So what you're saying is bank.ch, right? So like we're making a request to bank.ch with same site set to none. The path matches, the domain matches. So we're just going to send a bank.ch cookie, right? Now, what if we didn't properly build our web app? Then the attacker might be able to just, when we visit their page, just send a request to bank.ch/transfer funds, of this particular amount to this particular account, right? Server side, we have no way to distinguish whether we're talking to evil.com or bank.ch. There's nothing in the if what we're using is cookie to authenticate to user, there's no way for us to know whether or not this request was made by our code running in the browser or some completely evil page that the user happened to visit. right? So this is called a cross-site request forgery. It's because you can make requests cross sites, and because cookies are being sent, it looks like they came from the actual user. So like you can trick servers into doing things that they otherwise shouldn't. And you're going to find still many servers on the internet today that are vulnerable to these class of attacks. Now, same site cookie kind of changed this a little bit. So in the none case, right, we send cookie without taking who's making this request into account. But with the same site attribute, we're going to actually look at who's making this request. So the default now is lax, which basically says like, hey, we're only going to send cookies when we navigate the page, and that is a top level page, not even a nested iframe. So that's when we actually send cookies, even when we're navigating to a different origin, a different site, if that navigation is safe. So for example, if we click on a link and that's a get request, then we're going to actually send cookies as we would normally. But if we try to, say, embed an image the way we did in this example, the cookie won't actually be sent. It'll be treated as a cross-site request, so we're not going to send any of those cookies. So lax is the default, but you can turn on the paranoia knob a little bit and basically say like, actually, browser, what I'd like for you to do is only send cookies when the context that's making the request is of the same origin as, or the same site as the the destination URL and cookie, right? So this is basically being actually strict. This is actually being like enforcing real isolation of these cookies. The one ugly bit, and the reason we have lax as the default instead of strict, is because when you click on a link, you wouldn't actually send. Like if you go to say google.com and you have a list of search results and you're say logged into GitHub, when you click on a GitHub link, it will seem like you're not actually logged in because we're not going to send those cookies if we had strict mode on by default. That's why lax for navigations essentially sends cookies, because you want to basically give the user a reasonable experience of, you're logged in, so you don't have to like log in again. We just didn't know that this was your cookies were there and the browser didn't decide to send them. Okay, so let's look again at our previous thing with same site being lax. So this is what your browser is doing today. So if we include an image to bank.ch from evil.ch, and the bank.ch didn't specify same site equals none, then when we make the request, we're not going to send any cookies, right? So that's pretty awesome, right? So now like that CSRF attack where we transfer funds suddenly goes away, right? Like you have to go out of your way as the bank to make that attack feasible. Now, when we have, say, a link to bank.ch and we render this link and then click on it, then we actually do end up sending the bank.ch cookie because, again, we want to navigate to that page and make it seem like we were actually logged in if we happen to be logged in and had cookies for that particular page. Okay. But if we have that same link with same sites set to strict, which is probably what you'd want your bank to do, then in that case, no cookies will be sent again. And again, like if I'm being defensive and trying to build secure web apps, like one for a bank, I'd probably set same site equals to strict, because I probably don't want my users to click on links that may still contain potentially dangerous things that are then sent to my server with a cookie that authenticates them, right? I want to actually only like essentially treat the code that's running in my users' browsers as completely isolated from other web applications. Now here, this thing is called same site and not same origin. And what this basically means is the top level domain. So checkout.site.com is the same site as login.site.com, which is the same as site.com. So sites basically just look at the top level domain. So what this means is what we looked at before, that whole fill-in sheet of which cookies get sent where stays the same. And this is basically just a compromise because large sites, essentially, you'd want your mail.google.com and maps.google.com to be treated as the same entity because it typically is. So it's kind of a compromise. So we're kind of like losing a little bit of the origin boundary, but we're getting some benefits from these new attributes. Okay, so the last bit that I wanted to tell you about is the secure attribute on cookies. So if you put the secure attribute on cookies, this cookie is only sent when the server client communication is done over HTTPS. So what this basically means is we're not going to send cookies, like the browser is not going to send cookies to your website over an unencrypted communication channel. And this basically addresses one of the very early things that we like mentioned in the class, which is the network attacker. So what we want to make sure is that a network attacker can get our cookies. So if we serve our page over HTTP, we want to make sure that we're not sending cookies when we do that, because if we do, then the attacker can basically do anything they want, right? So first, they can just steal cookies if the server allows unencrypted traffic, we don't even have to actually wait for the user to go to that website. If you visit evil.com, they can just make a request, and if same site is set to none, then that thing will actually send the cookies. And if I'm on the network, I can just inspect those cookies. Right? If I'm on the network, I can inject JavaScript and get you to run JavaScript. So the short of it is, don't serve pages over HTTP. That's how we deal with network attackers. Okay, so that's all I got. Sorry for keeping you a little bit over. For those who went to watch the Angela Davis thing, then I hope it was fun. I'm going to try to hop on that. And I guess if any of you have not, now is the time. Go have fun. Thanks so much.